So here we are. Hopefully you understand the more simple related rates problems, because we're moving on to more bigger and better things. That's what we're gonna do. And so we have our first example. We have this picture. Maybe I'll draw a box around it. So we got this picture where a camera is trying to focus on a rocket, but the rocket is taking off. So the rocket is shooting up in the air, and then there's this angle of elevation for the camera, and that angle is going to keep changing because the rocket is going to go up and up and up and up and up. So this distance is going to change, this angle is going to change, and this distance is going to change. It's going to get longer and longer and longer. Same with this. This distance is going to always be 3,000 feet. And the problem says, suppose the rocket rises at 880 feet per second. When it is 4,000 feet up, how fast must the camera elevation angle, so theta, how fast must the theta change at that instant to keep the rocket inside? This is interesting. So the first thing that I'm going to do is I'm going to redraw a picture just so that it's a little bit cleaner with less detail. So I'll draw with nothing. I'll draw a triangle. No, bad triangle. I'll draw a triangle, and I know that this is 3,000 feet, and I can put it there because it remains 3,000 feet. This angle is going to be theta. That changes, so I name it theta. This distance, this changes, so I need a variable. Maybe y would work well because, well, it's y, like the y axis. All right, and then the hypotenuse, that's going to be changing as well. So maybe I'll label that h. I don't know if I need all of that, but we'll see. Okay, so now let's pick apart our problem. Suppose that the rocket rises at 880 feet per second. Well, the rocket distance from the ground is denoted with y, so actually from here to here, that's just the distance the rocket is from the ground. I just said that. So this 880 feet is how fast the rocket is going, which is how fast this side is changing. So I'll say dy dt. dy dt is the rate at which y is changing, and it's also the rocket speed. But it's not the rocket speed all the time, it's just the rocket speed when it's because it could be accelerating 4,000 feet up in the air. So this is actually at y equals 4,000 feet. That's just something to note. And then, so that's the rocket speed. What are they asking for? How fast must the camera elevation angle change? Okay, that's a rate, and it's the rate of theta changing. So the rate at which theta changes is just d theta dt. Okay, that's very nice. Okay, let's write down what we know. We know that I'll do this in green. I cut myself off. We know that dy dt equals 880 at the time of this problem, feet per second. We want to find out what d theta dt is. We don't know, but when y equals 4,000 feet? Okay. So remember, all those steps stay the same. Write out what the rates mean. We actually don't even need h right now, right? Because we're asked for just d theta dt. So how can we relate theta and y? Well, this is a right triangle, so I can just use my tangent function. Oh, I can also relate the 3,000 just because it's a number. So my primary equation could be tangent of theta equals opposite, right? Toa, SOHCAHTOA, opposite over adjacent. So I could say y over 3,000 And that's my primary equation. So that means all I got to do is take the derivative of this and see what happens. Something that I'm going to mention is that this tangent of theta, that's also equal to 1 over 3,000 times y. So now this is just a coefficient, or now it's more noticeable that it's a coefficient. So if I take the derivative, I got to use the chain rule. We're doing the derivative with respect to time. So, yeah, these don't agree. So I have to take the derivative like normal. So the derivative of tangent is secant squared theta. And then tack on a d theta dt. And that will equal 1 over 3,000. Derivative of y is just 1. But we tack on a dy dt. Okay. What do we do now? Well, we try to plug in stuff. I know that theta. I don't know theta. I know that this part, dy dt, that was the speed of the rocket, and that was 880. So that's 880 feet per second. Theta, I do not know, and I do not know d theta dt. But anytime you get stuck like this, you go back to your primary equation. That's something worth writing down. So I don't know what theta is, but I need to know what theta is. I don't know what d theta dt, but that's the whole point of this problem. So my primary equation. Look at this. I know that y is 4,000 at this time. So we'll reach 4,000 divided by that number, and we can just use the arctangent function. When does theta, like arctangent, do it in the calculator? So if we use the calculator, we get that theta equals, I'm going to be in radians. It's going to be 0.927 radians. I truncated or rounded to the third decimal place. So there we go. Theta's that. Ooh, beautiful, beautiful. So now we have secant squared of, I'm going to put the whole thing in, 0.927295218. I'm just looking on my calculator for that. Times d theta dt. I don't know what that is, but I don't need to know. That'll equal 880 over 3,000. So really, all I do is I see what this number is. I take the secant and I square it. That's the same thing as doing 1 over cosine, right? Squared. I'll write it differently. 0.927 squared. That's the same thing. So I do that with a calculator, and I get 2.7 repeating if I don't round at all, times d theta dt. We're on a roll. We're on a roll, baby. And so I will divide those two things. I will just divide, and d theta dt, is going to be in radians, radians per second. And that's just equal to, if I don't round at all, I get 0.1056 radians per second. I'm going to say radians per second. So that's how fast the camera needs to move. Geez, that was quite an example. Yeah. This is Sibling Rats.